So 1.5, we started last time about continuity, and check it out. I found several cool animations. This is the example of the hole. You see, limit is like pointing. It's pointing towards some kind of height. When x approaches a from the left and from the right, I can actually point at this. When x approaches a from the left and from the right, x is always smaller than a, x is always bigger than a. If on the height level of the function, that's out, if they meet from the left and from the right, giving you the same height, g in this case, limit exists. Left limit, right limit, they're friends, limit exists. Even though there might be a hole there. Because you see typical errors, it points at it, and it might never reach it. That's why it's called limiting position. It doesn't have to reach that place. And this one is a cool one. We're going to do it today and on Monday. Vertical and horizontal asymptotes are really cool too. So the previous one was discontinuity called hole. This one is infinite discontinuity. You will have answers in your homework like minus and plus infinity. This is how you see. X approaches a again from the left and from the right. F of x, you put a pencil on, and then if the pencil goes down forever, that's floor. Infinite black hole on the floor. That's minus infinity. If you put a pencil and it goes up forever, that's up into this time, infinity, that's plus infinity. Sometimes it can go both down, both up. Sometimes one can go down forever, and this one actually just stops somewhere. So they will be asking this kind of questions in 1.5 and 1.6, asymptotes and discontinuities. It's called infinite discontinuity for obvious reason, because it's infinite. So that is actually the most exciting ones. It has lots of applications, chemistry, physics, and engineering. It's really cool. Yeah?
Does that mean minus infinity is equal to plus positive infinity?
No. So infinity in general we define as any next point is still larger than the previous one. So forever it's keep growing. So infinity means infinitely large numbers. Minus infinity means infinitely large numbers but negative. So we actually...
I heard a lot of theorems depend on the assumption that the number system is cyclic.
Mm-hmm.
So
oh yeah, those are different cases. But in general, the question was if minus and plus are the same. Infinity is huge numbers, so we usually say minus infinity, huge but negative. We say huge negative numbers. And in general, it's up and down. So remember, in American language, they call it run and rise. Run are inputs or x-axis. Rise are f of x or y or output. So height is defined by the output. This is good, very nice kind of introduction. We wrote down last time, if you missed it, it's in my notes. What does it mean to be continuous? And let's continue from there. Continuous actually has like a very nice definition, which is literally this short. A continuous function at x is a function is continuous at the point x equals a if you have this. We wrote it down last time. Limit f of x at a matches with f of a. What's so special about it? Right? It's very nice, condensed definition, very elegant. We like to say it in math. It's an elegant definition because we have cases. Here you go. At a, you don't have to copy that, but at a, the function is continuous. To check that, I told you intuitively you can put a pencil, and if you never had to take it out of the paper, it's continuous. So should we have no holes, no jumps, no asymptotes. So at a, it's continuous. But at definition, you check step 1. I gave you steps. Is f of a defined? Let's see. F of a is over here. There's no hole defined. Is limit exist? For limit to exist, left limit need to be equal to right limit. Let's check left limit, right limit. They met. It's the same number. Limit exists. Check mark. That is not enough. They have to be the same number. What if this was a hole over here, but it was defined here? Now it's not continuous. So it's important then the filled up point is exactly at that location of the hole. So the last part is a definition. They should match. They have to be the same number. So this is an example of continuous function. How about this one? F of a is not defined. That's it. It's not continuous. It has a hole. You have to take your pencil out to go back. So even though limit exists, fails to hold the first immediately rule. This one, f of a exists. It's this one. check mark. Second check, we check left limit and we check right limit. What's the problem? They did not equal each other. They did not meet. They're not friends. Limit doesn't exist. Boom, failed. The limit failed to exist. And the last one is the most interesting one. I mentioned this one. F of A exists, check mark. Limit exists, check mark. So why it's not continuous? They're not the same numbers. So it's a hole that end up to be filled up somewhere else. In general, you put a pencil, you go through, you have to take the pencil out, put it in here, take the pencil out, put it back, and then keep going. So that's called a hole discontinuity, jump discontinuity, infinite discontinuity. The domain definition, we reviewed that. And then I found this cool picture, check it out. Removable discontinuity, that's a hole. You already have this, I just found a pretty picture. Infinite discontinuities, infinities. If it goes up forever, that's plus infinity. Down forever, that's minus infinity. Jump discontinuity, it literally jumps from one height to another height, up or down. And oscillating discontinuity, that's a rare case. We don't work with functions like this in this class, but actually they do happen with magnetism and lots of cool rare examples. The idea is it oscillates so much that you can never say that they even meet from the left to right. It just keeps going, and the denser you approach the point, the more the functions keep jumping or wiggling up and down. So that also means limit doesn't exist. That is what we did last time. Let's work on the example from your homework so you can finish your homework. Example 1. F of x equals to piecewise function, again, x squared minus x minus 2 all over x minus 2. This happens when x is not 2, because when it is 2, we have division by the 0. So then what happens when x is 2? Well, we decide to actually define it somewhere. And let's define it, let it be 1. Because originally you could not define, it's division by 0. So let's just make up some number. For example, it's 1. So everywhere else, it's a fraction of 2 polynomials. But at 2, it's just 1, constant. And the question is, find if it's continuous or not everywhere. And then we're gonna have some other additional stuff. Question. Is f of x continuous? C-O-N-T, it's a classical short notation for the continuous. Nobody wants to write down continuous all the time. Continuous for any x? Question mark. Do you know, at the beginning I was writing European x, which looks beautiful like this. That's how we write x when we learn math. And then I ask Americans if they like this one or this one more. And all my American students says, no, we like the cross one better. I'm like, yeah, but then when I want to cross it, how is it going to be like this? So what if I want to cross it? So I always found it's odd that you guys like this one more. I think our European style is more beautiful. Look how pretty it is. Isn't it pretty? Right, thank you. Extra credit. Solution. So I will do steps for you so you can just continuous or not for any x. I'll do steps for you to check. Step 1 is, we need to check what's wrong with the function first. And I see that x squared minus x minus 2 is fine. It's a polynomial. Polynomials are continuous everywhere. So idea first. Step 1. Polynomials are continuous for any x. For any x. So parabolas, cubic functions, 5th power, 17th power, they don't have gaps. They just nice wiggling functions going up and down like this, parabolas, lines. Those are all polynomials of different degrees. X squared minus x minus 1 are fine. X minus 2 is fine too. The fraction, what makes it tricky. At 2, you see division by 0. And also this whole idea of the piecewise function makes it interesting idea that something is happening over here. What is happening at x equals 2? So we're going to say that potential problem potential, let's call it point of discontinuity. Point of discontinuity. Who remembers what discontinuity is? It's not a tricky question. Yes? Yeah? No, I like what you said. Some more? Function is not continuous, yeah? Jumps. So you guys are all correct. Good job. Points of discontinuities, jumps, infinite discontinuities, holes. In general, we say points where function is not continuous, called discontinuous. This definition that relies on the definition of continuity. Why it's potential? Just because it has a piecewise function doesn't mean it has a hole there or a jump. It may be just a fancy way to writing it down. So it's a potential means we're going to be checking it. It's a candidate. We call it a candidate. In this class, we're going to have this terminology later. So potential of point of discontinuity, I did not finish. What is it? X equals 2. Something might be wrong. We're going to have to check it. So step 3, check X equals 2 using the definition, right? Or I will say via means using, right? Let me know if you don't like the abbreviation, definition. Using the definition. And the one I mentioned at the very beginning, step 1, step 2, step 3. We just reviewed it briefly. I put in different color. Here's the one. Step 1, let's check if f of a defined, if the limit exists, and then if it's the same number. Take a picture. Let's check that. And then you will help me with that, because I feel like I'm talking too much. So A, or whatever, I don't want to put it one more time, is f of 2 defined. Definition. Defined. Question mark. F of 2. Okay, let's answer the question. What is f of 2? Do you understand that? F of 2 is like in front of you. It's 1. Yeah. So the answer is yes. Yes. Check mark. First one, we passed this one. Step 2 is find the limit. What is the limit of f of x? Zoom in. As x approaches 2. So the thing is, like, we don't know yet. We need to figure it out first. And we cannot figure out right away, unless you can. But you need to figure out left limit, right limit, like you do all the homework right now. All this homework, 1.3, 1.4, 1.5, keep asking about left limit and right limit. So then we feel comfortable to put it on the test. One more time, left limit and right limit. So you practice and then you do well on the test. To do that, let's check left limit, which is called limit from the left, minus on the top of 2 means from the left. So x is less than 2. And then limit from the right. And if you missed my last class, I actually was explaining really well how I see piecewise functions and how it is not as scary as you think it is. So let's check left limit and right limit. The way I see a piecewise function and the way I like teaching it is this kind of visualization. This is my x-axis inputs. Something is happening at 2, so I'll put 2 here. And I will call the function number 1, a very unusual way, a function number 1. And the function number 2 is a function number 2. So at 2, I know it's a function number 2. Make sense? So in a circle, it means it's not a number, it's a name of it. You can do star and double star, or I and I. And what is happening from the left of 2 and from the right of 2? Which function do we use? 1. How do you know? Because before we had inequalities like these. Before we had this. So I know it's before 5, after 5, at 5. But now it says x is not equal 5. So how do you know that's the case? Can anyone try to justify it?
It's not equal to 2. The first function is not equal to 2.
So the whole function does not equal 2. That means everything else is a function number 1. But at 2, it's function number 2. Make sense? Yeah. I think some people nodding. People at the back, are you all doing fine? Okay. So let's do it. Then I know that the left limit is when x less than 2, and the right limit is when x greater than 2. And for both cases, I will be using function number 1. So I don't have to actually have calculation twice. It's a function number 1, and it's a function number 1. Because left limit is x less than 2, but approaches 2, and right limit is x greater than 2, but approaches 2. So I will continue here. It will be limit of f of x, and I'm nicely rewriting it, which is, I have it here. While I'm rewriting it, you go and simplify and finish the calculation. X minus 2. As x approaches 2 minus, and the same will be here. So technically speaking, I already know the limit will be the same. Let's see. So let's do equal. Oh, actually, I will continue and then move it later. What do you know? Let's people from the back. Let's bother those people. What do you guys know of? I believe you already started homework and you're very confident, right? It's fine if you're not, but you better start doing it because the deadline is on Monday. You don't want to get behind in calculus 1 class. So, people at the back, do you guys know how to simplify it? Well, the people nodding, that's nice. Factoring, I don't know what you mean though. Let me rewrite the bottom. I know that the denominator is the problem. At 2 it has division by 0. So I know I need to get rid of somehow x minus 2. It would be nice to cancel it out or change it. Usually it happens with another side of the fraction. Yes?
Multiply it by x minus 2 over x minus 2.
Multiply. So let me write down. It's kind of not the additional multiply, right? You do what? Who knows how to call it? Where?
Multiply by 1.
Conjugate. That's what usually we do with square roots. Split. That's a good word. I like the splitting. People at the back, what do you think? Splitting into what? X plus 2 and x plus 2. Minus 2 and plus 2. Do you know how to get it? This one I don't want to review it. It's quadratic formulas. Either you do the way you learn. Yeah? Oh. Yes? Oh, 1, 2. X plus 1. Thank you. Can anyone tell me, like, yeah, this lady wants to say, do you know how to get at this? Can you tell people how do we get this? See, like, you guys are so confident, but can you voice it? It's like, yeah, no, don't bother me. Quadratic formula, in the other way, we have, yes?
If you can multiply two numbers that add to, multiply two numbers that equal to C, those two numbers, if they add to B,
yep.
Then those are.
Yeah, that's called Vieta theorem, which is pretty cool. I always use that one too. So either you have the method when you multiply 2 or add 2 and gives you B and minus C and stuff. That's what I always use. Or quadratic formula. Basically, you find the roots, break it into products, okay? If you don't remember this part, you need to review it. I think I briefly reviewed it in lecture 0. But in general, this is very popular. So we have to keep doing that. Yay, the bad guy is gone. Bad guy is gone. Repeat. I gave you steps in algebraic ways of working with limits. Last step is always the same. Plug in and hope for the best. X plus 1 when x is 2 is 3. Yay. So that's how we work with limits algebraically. Guess what? This one will be 3 as well. The conclusion is, what's the limit? 3. It exists, like you said, because left limit equals to right limit. Now we just need to hope it's the same number as before. Is it? It's not. And that's how we know the answer. This function is discontinuous at 1.2. So f at 2, we found, let me put it in red, it was 1. And then does not equal limit at 2 as x approaches 2. Because this is 3. That means there is a hole. So we're going to write down answer. A means answer in black. F of x is not continuous or discontinuous. That's the same thing. Is not continuous. Parentheses. Discontinuous. That's the same thing. At x equals 2. And actually you can even name the discontinuity. Do you know the name? Jump is when left limit did not meet right limit. But yeah, good guess.
Point discontinuity.
Infinite, if you have infinity,
Point discontinuity.
it's a hole, yeah. It's a point discontinuity. Also called removable discontinuity. And right now we're going to learn how to remove it. But basically, this is what happened. F of A was defined, and it was 1. Oh, actually, I can sketch you a graph there. Why? I don't want to do that. Let's do it here. Let's sketch the idea. You can graph all this function and see what the graphing calculator tells you, or Desmos or Wolfram Alpha, but I know this kind of information. At 2, something is happening. We found that f of 2 is 1. Here it is, it's 1. But the limit as x approaches 2 from the left and from the right is 3. So whatever function was doing here, and there's a hole. Let me put a hole. F of 2 was cut out and put somewhere else. So f of 2 is over here. Let me make sure you know it's white. It is empty inside. That's called a hole or removable discontinuity. So let's write it down. It is a hole. I like the name hole, short and easy to remember. This is an official name of the type of discontinuity called removable discontinuity. Removable discontinuity. So now we're going to teach you how to remove it. So that means, let me move all of this. I will just, oh, it's fine. I'll just continue here. Now, example 1b. Do you guys have questions or comments? Yeah?
Sorry for jumping ahead, but the way to remove the discontinuity is it to determine a certain value of f of x that is equal to the left and right limit?
Yeah.
Is that the only way?
Yeah, we're going to remove it. So removing discontinuity means let's fix the problem. And now, good job for saying it, but luckily not many people heard you, so now I can ask it again. Yeah.
Maybe you said that all the polynomials are continuous for any x, right? But remember, if the discriminant is negative.
Discriminant? No, we don't count those. Discriminant is negative.
Oh. Then it will go imaginary.
Yeah, we don't go there. So I know what you're talking about. We don't go to imaginary numbers. Of course, in real numbers. So x, let me show you. Ax to the n plus bx to the n minus 1 plus la 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 plus whatever m. These guys are continuous on real numbers. And then if discriminant is negative, that gives you a not real root, complex root. So that we don't count those in this class. Yeah. So we usually say continuous everywhere in R, in real numbers. Yeah, but very smart. Of course you know. You know that when there's something wrong happens, you go to imaginary plane and then figure it there. That is actually very practical. Surprisingly, that is used a lot in engineering as well.
In iota terms.
Yeah.
So it will be removing discontinuities or assessing discontinuities where the discriminant is negative eventually in any of the calculus classes or not?
Not in this class. In upper classes, they show you.
Yeah.
When you see syllabus that mentions complex numbers, that's when they show it to you. They have to introduce it slowly. It's a very complicated, surprisingly very complicated idea to imagine things that you don't see. And it's surprisingly a very applied tool. It's everywhere in aerodynamics, magnetism, space science. So they slowly introduce it and you start applying things there. Good job, people, are very cool comments. In real numbers, polynomials are nice functions. We like them. But that's because in the real. They don't give you any troubles. Remove the discontinuity, I would say, in 1a, right? So let's learn how to remove it. So here's my sketch. Maybe I should make it prettier this time. My sketch is from the left and from the right, both limits pointed at 3, but actually at 2. The answer was 1. We don't like that. Someone cut out the point and put it not in the right place. So to fix that, guess what you should do? Put it in the right place, right? And then that's a very good answer. Let's put the point in the right place. Even if there is no point, actually, you can still fill in the hole. So I would say we should fill in the hole. and terminology is used, we should redefine f of 2. So solution. F of 2 is defined at 1. Let's means let us, right? Redefine f of 2. To do what? To do what? It's not make a function continuous. What else do you want to say? There's lots of things to say. To do what? To make function continuous, to fill in the hole. What did you say? To remove discontinuity. So that's all correct, right? Remove the hole, make it continuous. To remove this hole, redefine the function. So let's do to fix the problem. Life problem. I would say, which one do you like? I like to fill in the hole, I guess. That's like the least professional phrase, so I kind of like it the most. Well, let f of 2 be equal to what? This is not a tricky question. You just need to know how to answer it. To be what? 3. So I want to cancel f of 2 and put it in f. I want to cancel 1 as f of 2 and make it 3. So we cannot just fix the function and call it f. That's why we're going to call g. G of x now will be a function that we created from f of x, but now it is continuous. The top will be x squared minus x minus 2 all over x minus 2 when x is not 2. And then again, remember, we cannot divide by 0, so it's not like I can suddenly write down for any x. No, when x equals 2, there's still a problem. So what we're going to do, we're going to put a new cool value there named 3. This function is continuous. You can check it using all the steps we just did. Left limit and right limit give you 3. F of 2 is also 3. And I will write down, since f at 2 now equals limit as x approaches 2, f, oh, it's not f. Thank you. G of x, limit of g of x, x approaches 2, are now the same. Doesn't even matter which numbers. What's important is they're the same. The function is continuous. So put this in table. The new function, function g of x is continuous. That kind of stuff. So basically what we did, we filled in the hole, we removed discontinuity, we fixed the hole, we made the function continuous. All of those are synonyms here. That's why it's called removable. That's the only one that we actually can fix. Surprisingly, you cannot fix jumps. When I was learning this material when I was a freshman student, I was upset why we cannot fix a jump. You just take one function, move the other one up or down, and you're fine. Apparently that is a big deal. To redefining the height of a half of the function or a third of the function is not the same thing. You cannot do that. 1 point, a hole is fine. So that's kind of like interesting. What do you think about this? Can you do it now on a test and your homework? Yes?
I was just wondering, the only way that we can fill in the hole is to just like make a new function, right?
Make a new function, yeah. I mean,
we can't change the function, just gotta create a new.
You can say that you change it, but that's gonna be a little bit not professional. Yeah. The professional way to call it F1, for example, or F bar. Sometimes in the article you will see F hat, and that means it was changed. Yeah. But you don't, you know, in computer science, when you code, you say define F, be this is this. And then you redefine it again. That's not good. You created a different function saying that will be f, but different. So that's the idea here too. You don't mess up the previous information. Yeah, that is just more practical. Yes?
I'm a little confused about what part exactly fixes the hole in this.
Oh yeah, let me show you. It's not obvious. I'm actually happy you asked. I'm not convinced everyone understood it, so I'm glad you asked. Let's see. So we have x and y, 0 at 2. You don't have to keep copying it, but that's, I think it will be nice to explain it. we know that limit from the left and limit from the right pointed at the whole before at 3, and the point was 1. So what we did, we redefined the function, and we now say, you know, f of 2, notice not f, g of 2 now is 3. So we took a pencil and we filled in the hole. And now, if you take your hand and put a pencil on the graph, you will not have to take it out. You're going from the left, hitting f of 2, and f of 2 is still the same number, so you keep going. Unlike before, you're going, have to take it out, put the point, take it out, put it back, and keep going. Does that make sense? So we redefined the hole, we redefined the point, we moved it into the hole, it filled up the hole, now there's no jump, holes, discontinuities. And it was not a jump, there's no hole.
So what we basically did was, instead of taking some other point which they actually prescribed to us.
Yeah, we prescribed it, that's a good word.
So yeah,
Yeah.
we just plug it in, we would just brute force it in.
Yeah, we brute force it. I like, yeah, it's very nice. And I like prescribed, brute forced, kick it. I like that. That's a very good explanation. I should use those words too. Yeah, we just brute forced it. We redefined. That's when you feel very powerful. You just like, let me fix the function. Yeah. Yes. Thank you for asking. Yeah.
We can just redefine g of x as g of x equals x plus 1, right? Instead of splitting the function into parts.
G of x is, oh, that's interesting. If you simplify completely. Yeah. So the whole, that's a good question. I probably should not go there, not to take too much time. But he's right. Can we just redefine it as completely the simplified version of it? Where is it? It's here. When we simplify, the whole point of division by x minus 2 was because of the whole. The moment we fixed the whole, technically speaking, now we just left with x plus 1. So, good point. Yeah, we can do that too. Good job, people. Yeah, the question?
Can we get another example, like, of redefining?
Yeah, we can do more. Let's move on to the end of the class. Let's see. I think I also have videos, which is nice. Let me show you the Intermediate Value Theorem, and then we can do more examples. And I want to show something from your homework anyways, so that's good. Intermediate Value Theorem, I want to mention it. I like more questions, you know. Because, I guess let me write it down from scratch. It's called Intermediate that's E-D-8 Value Theorem. Who knows what the intermediate word means? What does it mean? In the, between, middle, right? Yeah. It's not necessarily in the middle, but it's between. Very good. Thank you. Intermediate Value Theorem. Very interesting. It's a pretty cool concept. It's pretty important, but to be honest, not in this class. We do introduce 2 intermediate value theorems right now, and then later in the integrals. It's very important in math and applications, but not in this class. So just you will see it barely any homework about this. If the function is continuous, let f be continuous on the closed interval A and B. What does it mean to have a closed interval?
A and B included.
Very good. A and B included. People at the end, you know, A and B should be included too. That's called closed interval. Because if it's open, then A and B are not in a domain anymore.
So basically the whole is filled in the graph.
The whole is filled, exactly. Everything is filled up from A to B. And capital N is a number between double E, f of A and f of G. That's the height. So it's between 2 heights. But also it's not the same. Let's make sure, but f of A is not the same as f at B. Then there exists. For you to know in math, we have one symbol for this whole thing. Then there exists. It's the mirrored E. That's the term. You will learn it later when you get to proofs. That means then there exists. So very convenient. One term just says all of this. Especially in Russian, Ukrainian language, all those words are very long. So nice to have a short math notation. A number C that belongs, and then let me see if you remember what that means. C belongs to the open interval A and B. Let me finish writing and then I'll ask you. Such that f of C is n. Super confusing, who knows what it means? And now I'll explain you what it means. Yeah?
If f of A and f of B exist on a closed interval and any number in between them will also exist.
No, very good. And any number between them also exists. Yeah, that is so good. So I have several questions. Who remembers what does this mean? I call it C with a tongue. Belongs to, included. So you can write down belongs to, or from, belongs to. That one you should know it. Then what does it mean to have open parentheses here, not brackets? Open interval, that means A and B are not in the domain anymore. So from closed interval, now we're talking about open interval. And the final part is not obvious, so I'll explain you that. Here's the idea. I like giving example of your age. So example, function of your age is a continuous function. Super simple to understand that. In 5 years, guess what? You're 5 years old. And after you're born, like while I'm talking in those 35 seconds, you're 35 seconds older. So it's a very continuous function. You cannot jump over even a microsecond unless you are traveling in time or dissociating. That's a good joke. But in 90 years, you're 90 years old. So that makes sense. And that's why this theorem works really well on this example too. But if anyone ever asks you, what does it mean? What kind of functions are continuous? You're like, well, parabola, sine and cosine. The cool one is the one that's not defined everywhere, but it's your age. It's a nice linear function. It's very straightforward. You can predict in 200 years, it'll be 200 years old. Even though you're dead, you still can count years. So here's the function. And then we have A and B closed. So A and B are included. Then we have some kind of random C, not necessarily in the middle, but it's definitely between A and B. And C belongs to the A and B without the edges. Yeah, it says C should be between. See? We don't want to have end points. Then they say N. We're going to have N first. Here's my N. N is between two heights. N is between f of A and f of B. Here's f of A. F of A. Here is f of B. F of B. Keep going, keep going. N is between those. It's basically, if I take a ruler, look how awesome that is. Look at this, look at this. I'm taking a ruler, and then you don't have to be that beautiful. It's just kind of, I like it. Here's my N. Isn't cool? Surface Pro is my favorite investment in the teaching. So it's in between those two heights. Here's one height, another height. Actually, I should not put it here. Let me put it F at B. So we say, okay, I notice that right now, many of you are 18 years old. I'm like, yes. So this is your age. That means 18 years old is the output of timing. So input will be years to count. So that means between A and B, for example, A is when you were born and B maybe when you moved in to the dorms, not necessarily when you died. There was definitely a moment in time when you were, say, oh, that's better even. If you are 0 years old, and then you're 25 years old, and say your functions keep growing, right? So continuous. Right now, you're 18. That means there was definitely moment in time, when it was a year, 2013, and whatever it was a month, when you are 18. Or if you want to see it this way, there was definitely a moment in time between A and B when you were 10, or when you were 11, or you were 5. So it cannot jump through. The intermediate value theorem is always taught in the chapter of continuity because it's exactly what it means. Functions are continuous and they don't do anything crazy. And when they're continuous, You can predict what happened in the future, in the past, so I know how old you will be in 25 years. And you can definitely say in between you had the same age. You could predict what age you had. I guess that's a better way to say it. So that's also cool with the speed. When you're driving a car and your speedometer goes up and down, up and down. The policeman stops you, says, oh, you were driving 90 miles per hour. That means somewhere between you started driving and then got stopped, there was a moment in time when you were driving 90 miles per hour. That's kind of the idea. So we will be learning derivatives in a couple weeks, and that's kind of the idea here. The policeman can guarantee that even though he never saw you driving 90 miles per hour, the speedometer showed you, and you never even finished driving an hour, miles per hour. You don't drive per hour. The policeman just saw you right now. So that theorem is used for speedometers, calculations, and stuff. That's kind of the idea here. Let's see, I think there was a cool animation here.
So is it almost something like the value at that instant?
Yeah, so basically, idea I would say it can guarantee it exists. Check it out. So I would say this also will go to derivative soon, so that's a secant line. But there it is, the functions are continuous. I don't have to take the pencil out to keep moving from A to B, and if both ends are moving, you can guarantee that they're going through the whole function without jumping through. That is, I guess, my point here. Finally, let's see. The last thing I wanted to mention is domain. Let's see. I saw it in your homework, and I thought you might get confused or not. But that's the last thing is integral notation for domain. Let's do that. Example 2. So your homework says this f of x equals. Let's do, I guess, this one. It's open. X minus 7. I like helping students by showing some homework problems to speed up your progress. X plus 5. Like so. And they ask you to use interval notation. Use interval notation. This is something they teach in pre-calculus or even college algebra, but many of you don't remember this, so that's fine. Interval notation to indicate the largest set where f is continuous. For domain, I would say for domain. Solution. So you want to show where the function is continuous. That means you find where the function is not continuous and excludes it from the domain. The easiest way we like to show it is x should not be what? Negative or positive? 2. And x should not be negative 5. That is not the interval notation though. So they want you to practice the interval notation. This is a short way to say it. I like this way the best. It's fast, convenient, people know what you mean. But that's kind of saying, don't eat this bad apple, don't eat that bad apple. So how many good apples are on the table? You don't kind of define something by excluding things. So they want to show what are all the safe points here. What is a domain? So you write it down like so, domain, or a function is continuous on. You do parentheses. Oh, let me, I guess, ask you. Who wants to figure this out? It's not like a very, yeah, I like people at the back. Let me have them. Yeah. Negative infinity, heard you that, yes? Negative 5, close open parenthesis, yes. The U means union, amazing. Amazing. You did not forget to not to skip, that's good. 2 U. Amazing. Splendid. I was watching British shows. It's splendid. Thank you. So don't forget this guy in the middle. See, amazing. So if you remember this, you should be fine. That's how we show domains. Yeah.
Can we just say open parentheses minus infinity comma cos of infinity minus of set of 2 comma minus 5?
That's correct, but usually people don't do it this way. Again, usually people don't exclude things. They just show everything that's included instead. Yeah.
X belongs to R minus 2
2 and
yeah. minus.
Yeah, that will be good too. But they want parentheses. But all of this is correct. I would say two of your ways are more interesting and more complicated. So they want the simple way, the one they teach in pre-calculus classes. Good job, people. Don't postpone your homework. Start right away. Finish by Monday.